So there is a changes in internal energy of the system is equal to the sum of the work done and heat absorbed by the system. The above expression is a mathematical representation of the first law. This statement is a corollary of the following general statement. The extent of convertibility of one form of energy into another form cannot be predicted. Hello everyone, this is Harshita Bhavasar from Vidhyaashram PU College, Temple of Excellence. Today we are starting up session 3 from the chapter Thermodynamics. In this class, we will discuss about the first law of thermodynamics and enthalpy. How the first law of thermodynamics has been stated, and also what are the expressions will be used for the first law of thermodynamics and what is enthalpy, we will discuss in this session. Now that we have an understanding of basic concepts of thermodynamics, we will discuss the principles or laws of this fascinating branch of science. Already we have seen the introduction part of thermodynamics, terminologies of thermodynamics and reversible and irreversible process, and also what is heat, work, energy, the different kinds of system, different kinds of processes we have seen in our 2 sessions. In this session, we will discuss about the first law and also the overall concepts of thermodynamics and also what are the factors favoring for the first law of thermodynamics. These laws are not theorems with deductive proof but generalization of several experimental and observed facts. See, in mathematics and other subjects, we have so many theorems to prove it, those theorems, and we have so many steps also. But this is a physical chemistry subject, so based upon observations, based upon experiments, so many expressions have been given but not by theorems or any kind of proofs for that theorems. The first law of thermodynamics was proposed by Joule in 1851 as a corollary of conservation of energy. The first law of thermodynamics was proposed by Joule in 1851 on the concept of conservation of energy. He was the first scientist who proposed this first law of thermodynamics. The conservation of energy principle states that energy can neither be created nor be destroyed but can only transform into alternate forms. From so many years we know that the principle of conservation of energy is nothing but energy can neither be created nor be destroyed, but it can transform into different forms. Consider a closed system containing an ideal gas to which Q amount of heat is given from the surroundings. Now we are considering one system. For that system containing ideal gas, Q amount of heat, Q is nothing but heat we are giving from the surrounding, means from external surrounding to internal system has been given. According to the first law, heat cannot be lost. A part of the heat absorbed goes work, that is W, in such a way that heat absorbed by the system increases in internal energy plus work done by the system. According to first law, what they are saying, heat cannot be lost, but a part of heat will be absorbed and goes with the work W in such a way that heat absorbed by the system, whatever the heat absorbed by the system will be equal to increase in internal energy plus work done by the system. This is heat, this is internal energy, this is work done by the system, that's why minus W. Therefore, internal energy Q plus W according to IUPAC sign convention, more precisely first law can be stated as follows. The change in internal energy of the system is equal to the sum of heat energy given to the system and energy given to the system in the form of work. Okay. This is the overall sign convention. If we take delta U in the left hand side, what will happen? This coming to the right hand side, this W will become plus, and more precisely the first law can be stated as follows. What they are telling, the change in internal energy, here delta is present, so there is a changes in internal energy of the system is equal to the sum of the work done and heat absorbed by the system. Then mathematical expression for the first law of thermodynamics. Consider a system whose internal energy is U1. Okay, consider a system whose internal energy is U1. if the system is supplied Q amount of heat, for that system, if they supply amount of heat that is Q, the internal system energy of the system, what will happen? U1 plus Q, because this is internal, this is heat. Now, if work is also done on the system, what the final internal energy will become? On the same concept, work will be done. For that, U2 it will become U2 equal to U1 plus Q plus W. This is the work done on the system. Then it will become U2 equal to U1 plus Q plus W. U2 minus U1 equal to Q plus W, because they have taken here. Then delta U equal to Q plus W, that is internal energy will be equal to heat plus work done. How this equation has been arrived? They have shown here. They have already told there are no theorems to prove. On the basis of experimental observations, the expressions are coming on in a flow. This is how it came. The above expression is a mathematical representation of the first law. This statement is a corollary of the following general statement. This is the expression for first law of thermodynamics. Total energy of an isolated systems remain constant. Okay. Universe is an isolated system. The energy of the universe is conserved. The energy change in the system and its surroundings are equal in magnitude but opposite in sign. If isolated means no energy and matter will be, changes will take place. That time, if you consider universe is an only isolated system, then energy of the universe will be conserved. Obviously, the energy change in the system and its surroundings will become equal in magnitude but opposite in sign. It is impossible to construct a perpetual motion machine of the first kind, that is a machine that does work continuously without a consuming fuel or some other source of energy. It is completely impossible. Without a fuel, a machine cannot run only. Okay. Next, Q and W as a path functions. How that Q and W as path function it is working? As already stated elsewhere, work and heat, that is Q and W respectively, are path functions because the amount of work done or heat loss do not depend on the initial and final states of the system. We know what is path system, we know what is state function, everything. Path function means which path the reaction has been taken place. But here what they are telling, the amount of work and heat loss do not depend on the initial and final states of the system, but depend on how that final state has been reached. That is why it will act as a path function. Q and W are positive if energy is gained by the system as heat and work respectively. When the Q and W will be positive sign when the energy is gained by the system. When Q and W, that is heat and work done, are negative, energy is lost by the system as heat or work. Therefore, Q and W are called energy in transition and have their role only during the process. They will call it as energy in transition. Transition means changes will be taken place. When it is positive, energy taken by the system. When it is negative, lost by the system. So, transition is taking place. So, it will be called as, overall call it as energy in transition, have their only role in when it is process is going on. Next, mathematical representation of first law of thermodynamics. When a system absorbs heat, that is Q, and receives work W, the change in the internal energy U of the system is delta U equal to Q plus W. We know this, and let it be equation 1. This is mathematical expression for first law of thermodynamics. If the changes are very small, that is del U equal to del Q plus del W, what will happen? Del Q minus P dV will take place. If the process is carried out at constant volume, then expansion work is not possible. Del U equal to del Q, that is constant volume. Okay, and if the change is measurable, delta U equal to QV. This is the equation 4th. Hence, internal energy change in a process is equal to the heat energy absorbed when the same process is carried out with constant volume. By taking the first law of thermodynamic expression, they have concluded that internal energy change in a process is equal to the heat energy absorbed. How much of heat energy has been absorbed by the system, that much of internal energy will be keeps on changing when the same process is carried out with constant volume. Heat is absorbing, system is there, internal energy is getting changed, but the volume was in the throughout process it was constant. Only internal energy and heat is variables. Next, limitations of the first law of thermodynamics. After seeing those many points of first law of thermodynamics, there are so many limitations also. The first law does not indicate the direction of a reaction. It doesn't show the direction of reaction. The extent of convertibility of one form of energy into another form cannot be predicted. How much the extent of convertibility, how much extent it can convert, it cannot show properly or it cannot predict it properly also. First law does not explain why natural spontaneous processes are irreversible. So many natural spontaneous reactions are taking place in our daily life. Why it is irreversible, it doesn't explain. First law does not differentiate between the spontaneous and non-spontaneous processes. Spontaneous means suddenly, non-spontaneous means slowly. The difference between these two processes, it doesn't explain. So, these are the limitations of first law of thermodynamics. Next is enthalpy. Most processes, physical or chemical, including those that takes place in living systems, occur at a constant pressure. Most of the physical and chemical processes will be carried out within the system. Majority of reactions in the laboratory are carried out in open beakers, flasks or test tubes, that is the reacting system is open to atmosphere at constant pressure. Yes, in so many, in our labs only what we'll do, test tubes will be open, beakers will be open, in that we will carry out the reactions because constant pressure will be there and it will be reacting with the environment also. The heat changes occurring during such reactions may not be equal to the internal energy change. Whatever the color changes will be observed within the reaction, it is not dependent or equal to the internal energy changes. Enthalpy is the total heat content of the system at constant pressure. What is the enthalpy? It is the total heat content of a system at constant pressure. It is mathematically defined as H equal to U plus PV, that is pressure and volume, where H is the enthalpy. It is the sum of internal energy and pressure, volume, work. Like internal energy, enthalpy is a state function, an extensive property. It is a state function and it is an extensive property also. It is measured in joule or calories. The measurable quantity of enthalpy is joule or calorie. The absolute value of enthalpy cannot be determined, but change in enthalpy during a chemical process can be measured accurately. Like the unit it will be, cannot be definitely we can give, but the change in enthalpy during process can be determined accurately, not precisely, accurately it can determine, but there is no finite value for the enthalpy. Delta H equal to H final minus H initial, because it is a state function. You can see the two states where it is initial stage and the final stage. It is not a path dependent, it is the final and initial stages dependent. Enthalpy change of a process is equal to the heat supplied to a system when the same process is carried out at a constant pressure. What is enthalpy? We understood the heat content, the total amount of heat content. So, whenever the process is going on, whatever the heat will be supplied to the system, then automatically enthalpy will also get changed at the constant pressure. Whenever the heat supplying is stopped, the enthalpy will change, will not change. So, it will also show at the constant speed of the heat. Characteristics of enthalpy. Enthalpy is a state function. Enthalpy change does not depend on the path followed for the change, but depends on the initial and final states. Yes, It is a state function. It doesn't depend on the path of the reaction proceeds. It just depends on the initial and final stages of the reaction. It is an extensive property as its value depends on the quantity of the system. Extensive property means this property depends on the quantity on the system. A change in enthalpy of a system is equal to the heat released or absorbed by the constant pressure. Whenever the enthalpy is going to change means we have to understand either the heat has been absorbed or released by the system, because the total amount of heat only will be considered as enthalpy. It is a measure of the energy of the system that can be released as heat. Relationship between delta H and U means enthalpy and internal energy. Consider a equation H equal to U plus PV as equation 1. This is enthalpy, and with the changes they have written delta H equal to delta U plus PdV plus VdP. At constant pressure, that is dP equal to 0, VdP equal to 0, what will happen? Delta H equal to delta U plus PdV will happen, correct? For measurable changes, delta H equal to delta U plus P delta V will be the equation. For a chemical reaction involving at least one gas, P delta V equal to delta NgRT, where delta Ng is the difference in the number of moles in the gaseous products and reactants. This delta G is the difference in the number of moles in the gaseous states of products and reactants. That's why delta Ng equals number of moles in gaseous of products minus number of moles of gaseous in reactants. So what will happen? Therefore, delta H equal to delta U plus P. For P will be equivalent to delta Ng, right? RT. So V equal to RT. This equation will form. This is the most important equation. Next, heat capacities and their relationship with internal energy and enthalpy. Molar heat capacity of a substance is the amount of heat required to raise the temperature of 1 mole of the substance through 1 Kelvin. The molar heat capacity we are understanding now. What is that of a substance? It is the amount of heat required to raise one temperature of 1 mole of a substance through 1 Kelvin. If you molar means 1 Kelvin will be present, 1 mole will be present. To raise one temperature of the 1 mole of substance, you have to reach through 1 Kelvin only. The two different ways of adding energy to the substance leads to heat capacity at constant volume and heat capacity at constant pressure. There are two ways in which adding energy can be done. See here, constant volume QV by N delta T, constant pressure QP by N delta T. The SI unit of both is joules per Kelvin per mole. A large value of heat capacity means that for a given amount of heat, the increase in temperature will be very small. This increase in temperature will be very small, but the amount of heat will be done very quickly as increase in the temperature. The relationship between pressure and constant pressure and constant volume for an ideal gas. At constant volume, the heat capacity C is denoted by Cv and the constant pressure, this is denoted by Cp. Let us find the relationship between the two. We can write equation for heat is Q at constant volume as QV equal to Cv delta T equal to delta U. At constant pressure, Cp delta T equal to delta H. The difference between Cp and Cv can be derived from an ideal gas equation, that is, for a mole of an ideal gas, delta H equal to delta U plus delta PV, delta U plus delta RT. We have taken PV equal to RT, so delta has been taken out, delta U plus R delta T, therefore equal to delta H equal to delta U plus R delta T. On putting the values of delta H and delta U, we have Cp delta T equals Cv delta T plus R delta T will become. See here, on taking out Cp equal to Cv plus R, Cp minus Cv equal to R. It will become the overall equation. Now Cp minus Cv equal to delta H by N delta T minus delta H by N delta T equal to R. R they have taken as common. For an ideal gas, its molar translation energy is E equal to 3 by 2 RT. For an ideal monoatomic gas, and the energy that changes with temperature is its translational energy, that is delta U translational equals to 3 by 2 nR delta T. For an ideal monoatomic gas, Cv equal to delta U by N delta T equal to 3 by 2 R equals 3 by 2 into 8.314, this is R, that is gas constant. This is the constant value of R, 8.314 equal to 12.47 joules per Kelvin per mole. After getting this one, that value will come. Cp minus Cv equal to R, and so for monoatomic ideal gas, Cp equal to Cv by Cv plus R, 5 by 2 approximately 21 joules per Kelvin per mole will come. In case of diatomic gas molecule, in addition to the 3 translational motions will come. 2 means 3, 3 means 4 translational energy will come. So the molecule shows rotational motion about its center of mass in mutually perpendicular directions and independent ways. The contribution of each of these motions for specific heat is 1 by 2 R. See here, Cv equal to 3 by 2 plus 1 by 2 R plus by 1 by 2 R plus 5 by 2 R, and Cp equal to 7 by 2 R. By taking LCM and all, if you calculate, it will come 7 by 2 R. This is true and for any linear polyatomic ion molecule. This will be the constant for any polyatomic molecule. In case of polyatomic non-linear molecule, Cv equal to 3R, Cp equal to 4R. The heat capacity ratio can be measured. Experimentally, it is denoted by Cv by Cp equal to gamma. Gamma equal to Cy by Cp. Since Cp is greater than Cv, the heat capacity of gamma is the number of greater than unity. The value of gamma provides the information about the atomicity of the gas. Nature of gas, this is heat capacity of pressure, this is capacity of volume, this is gamma at lab temperature. See monoatomic, 5 by 2 R, 3 by 2, this is 1.66. Diatomic or polyatomic, which will be in linear, 7 by 2 R or 5 by 2 R, 1.44. Polyatomic non-linear molecule, 4 R, 3 R, 1.33. These are the relationship between Cp and Cv with the overall molecules. Next, work done in an adiabatic process. In an adiabatic process, no heat exchange takes place between the system and surrounding, that is Q equal to 0. Therefore, the first law equation, that is du equal to dq plus dw, becomes du equal to dw, because this will be 0. We know that delta u equal to dqv equal to ncv dt, delta w equal to ncv dt. If the temperature changes from T1 to T2, because here no heat is present, so the temperature is getting T1 to T2 during an adiabatic process, we can write by the integrals of dw equal T2 to T1 ncv dt equal to ncv T2 by T1 by dt. So work done, what will happen? W equal to ncv T2 minus T1 equal to ncv delta T, this is the change, and Cp minus Cv equal to R. Cp by Cv minus Cv by Cv plus RCv. Gamma minus 1 RCv or Cv equal to R by gamma minus 1. After all the calculations or derivations have been moved to the further steps, W equal to Nr by gamma minus 1, R equal to P2 V2 by Nr minus P1 V1 by Nr equal to 1 by gamma minus 1, P2 V2 minus P1 V1 equal to PV equal to nRT, or T equal to PV by Nr. This equation is must and should, you have to understand. This is very much important. In the next session, we will discuss about the relationship between P, T and V for an adiabatic processes for an ideal gas. Means in the relationship between pressure, temperature and volume in an adiabatic process for an ideal gas. Measurement of delta U and H, that is internal energy and enthalpy, how can be measured. I hope you have understood completely what I have taught today. We'll meet in the next session. Thank you.